Okay, so in the last two lectures, we are going to talk about inflation. Which is a period that we think, a period in the cosmic history that we think it happened, it took place before the hot phase of the universe. So let us understand what is the motivation for introducing this phase, this additional phase. So to understand the motivations for this phase, we should discuss some puzzles with the hot Big Bang cosmology. So what are these puzzles? One of them is called the flatness problem. So we are going to discuss some weird things, puzzling facts about the hot Big Bang cosmology that in the past led cosmologists and physicists to introduce, to hypothesize that there is another phase before the hot Big Bang. So one of them is the flatness problem. What is the flatness problem? So let us talk about the cosmological parameters, in particular omega k. Right. So if you remember omega k, we defined it as minus k over h squared a squared. And this is a quantity that if we measure it today, or we do measure it today, and we actually put constraints on it, we haven't detected any non-zero value, but we have constraints on omega k today, which is of order 10 to the minus 3, the absolute value of omega. So it's a tiny value. It's observations are consistent with 0 omega k. Universe, the FRW background being the spatially flat. Okay, so now let us ask about the time evolution of this quantity. So let us imagine we define omega k as a function of time. So take this quantity and evaluate it at different times, as if we have observers who live at different times or at earlier times, and they measure omega k. So people similar to us, or maybe not so similar to us, but who lived at earlier times, or cosmologists who lived at earlier times and try to measure omega k. And they are infinitely powerful to do this measurement. So what would they observe? We should understand the time evolution of this quantity, right? Now, for most of the past history in the hot Big Bang phase, we were either in matter domination or in radiation domination. The lambda domination happened very, very lately at z of order something less than z less than 1. So for most most of the evolution, it was either matter dominated or radiation domination. So let us therefore stick to just a single single component FRW and see how this quantity evolves in time. So in matter domination, what do we have? We know that H is equal to H naught times A to the minus 3/2, right? So H squared is proportional to rho. In matter domination, rho goes as 1/A cubed, therefore H goes as 1/A to the 3/2. Which means that, so say now, let's use this and evaluate omega k at matter radiation equality, or estimated at matter radiation equality. Then omega k at equality should be equal to omega k today. So what happens if I plug in, in fact, I should have written just H squared. So H squared is H naught squared times A to the minus 3. Therefore, omega k is proportional to A during matter domination. So this means that at equality, equality happens when Z is over the 3,500. So that that means that since omega k goes as A, this should be 1 divided by 1 plus Z equality, which should be something over there less than 10 to the minus 3, again in absolute terms. So we don't know the sign. Sorry, 10 to the minus 6. So we have 10 to the minus 3 for omega k today, and then Z equality is of order of 1,000. So we get something over the 10 to the minus 6. Okay, then we are in the radiation domination phase. In radiation domination, we have H squared equals H naught squared A to the minus 4, which tells us that omega k will be proportional to A squared. So now let us go consider temperature, a very high temperature. So go to very early times in this radiation domination. So as we go to earlier times, we remain in this, or we imagine that we remain in this hot phase of the universe. So we remain in the radiation domination phase. We go back in time to temperatures of order of, let's say we go to the temperature of order of God temperature. T God over the 10 to the 16 GeV. So you will hear a lot about the God scale in the discussion of inflation. This is partly for historical reason. It's because at the time when people were thinking about inflation, the grand unified theories were very popular. So that's why everything was being compared with the God scale. But well, it's useful to have some number in mind. So let's go to temperatures of order of the God scale. Now we know that up to the number of degrees of freedom is changed by at most 1 or 2 orders of magnitude. The temperature goes as 1/A. So therefore, we get omega k God is omega k equality approximately times A squared, which means that it will be omega k equality times T equality divided by T got square. So this, what would be this number? This will be, so T equality is about 1 electron volt. And T got is 10 to 16 giga electron volt, which is 10 to 25 electron volts. So if we plug in numbers, we get something like 10 to the minus 28 to square. Ten to the minus 56. I write it in this way for a reason that perhaps becomes clear later. So this is a very tiny number. Now I made a lot of approximations to get to this number. Like I didn't take into account the change in the number of relativistic degrees of freedom. But as you see, it's such a small number that it wouldn't matter that much. If I included those, it would perhaps change it by a few orders of magnitude, but it is so incredibly small that doesn't change the fact that it's very puzzling. Why is it puzzling? Because it's not obvious why the universe had to be so extremely flat at those early times. If we imagine that the initial condition for the universe was set at that time. So let us draw the space-time diagram. For hot Big Bang cosmology. So this is supposed to be the Big Bang singularity. So if you imagine that this Big Bang singularity is somewhere around Gauss scale, maybe earlier. If the initial condition for cosmology was set at that time, it's not clear why should omega k, the spatial curvature of the universe, should be so close to 0. Why should it be tuned to such a small value? So this is called the flatness problem. Why is omega k initial so small? Any question about this? Of course, it's not a contradiction. It's just puzzling. It's a question about the initial condition. Of course, initial condition could be anything. So there is no contradiction with one particular choice, but yeah, it's just puzzling why it was so small. Okay, so now let us discuss the other problem, called the horizon problem. So now I can use again this picture for the conformal diagram. So now let us imagine that ourselves sitting here, and we see. So we make cosmological observations, and for instance, we look at the CMB photons. So where do they come from? They come from the last scattering surface. So that would be the surface at some early times at Z of order of 1,000. Is this last scattering surface, and we have our past light cone that intersects with the last scattering surface. Now so therefore we see photons coming from very far away regions in the universe at that time. So these different points on this last scattering surface. These points, now it's kind of obvious in this diagram that these points, many of the points on the last scattering surface, were not in causal contact with each other. So if I look at the past light cone of different patches on last scattering surface, I can divide it into several patches that were not in causal contact with each other in the hot Big Bang cosmology. Meaning that if the initial time is here, then they never had a chance to, these 2 points never had a chance to communicate with each other. However, what we see is that the temperature fluctuations of CMB is extremely small. So delta T over T is of order of 10 to the minus 5. So the temperature at different points on this last scattering surface is to a very good precision is homogeneous. And this is called the horizon problem. The question is how come these different patches, which were never in causal contact, ended up being so similar, so homogeneous? You see that it's not that they are in an exactly uniform and homogeneous universe. There are fluctuations. So it's not a symmetry that fixes it to be homogeneous, but they are extremely close to being homogeneous. So this is the horizon problem. Causally disconnected patches. Now we can estimate the number of the patches that we have in here. The number of these causally disconnected patches. So this is one of the homework problems. So you see that there are many of them, and we have order thousands of them. And again, this is a question about the initial condition. So as in the previous case, it's not a contradiction. So in principle, it's just a particular choice for the initial condition. However, it is puzzling why this happened to be the case. It didn't have to be like that. And it seems that there were many other choices, and one wonders why this happened to be the case. So again, it's a puzzle, but not a contradiction. This is very common in this context. Again, we don't have contradictions. We have something which is called naturalness problems. But naturalness problems apply to the, or naturalness questions apply to the initial condition. Why the initial condition was like this and not more generic. So this is the kind of puzzles that we have with the hot Big Bang cosmology. Okay, any question about this horizon problem? So one can also ask, but there are other problems. Like another important problem that is usually mentioned is the monopole problem. Again, this is because at the time God theories were grand unified theories are very popular. And there one would expect the formation of monopoles, which were not observed. So then one other question was why don't we see any monopoles, magnetic monopoles? But I think these are enough puzzles. We don't need to discuss that. Another question that one can ask is a more quantitative question, which is that we discussed the initial condition for the perturbations in our cosmology. And we said that we have good evidence that these initial conditions are adiabatic. These are adiabatic initial conditions. Let me remind you this. If we, for instance, go to the hot phase to radiation domination, that would correspond to having fluctuations of the temperature at different patches, at super horizon scales, which correspond to having identical histories at these different super horizon patches, except that they are shifted with respect to each other. So a more quantitative, and we have observation that for the spectrum of those initial fluctuations, we know that at least in some range of scales, they have they are approximately Gaussian and approximately scale invariant. So one could ask a more quantitative question of what gave rise to these initial approximately Gaussian and approximately scale invariant perturbations, which we observe today. These are perturbations which have very tiny amplitude, about 10 to the minus 5. So as we will see, this inflation was invented as a model that solves these puzzles with hot Big Bang cosmology, but as a bonus, it also predicts or explains the origin of these adiabatic fluctuations, which we are observing, and allows us to put interesting constraints on the models of inflation. Okay, so maybe I write something here. So the other thing is that what is the origin of approximately Gaussian and the scale invariant adiabatic initial condition. Okay, so now let us discuss how these problems, these puzzles could be solved. So we first discuss the solution. So let us first discuss the flatness problem. So we said omega k, which is minus k divided by a squared h squared. So this is the object that we see. It is in the hot Big Bang cosmology. It's something that grows in time. So if we go back in time, it decreases and decreases by many orders of magnitude. And today it is small, so at the early times it becomes incredibly. So let us remember that this object a squared h squared is something that we encountered before. We defined this co-moving Hubble rate. This was a prime over a derivative with respect to conformal time. And this 1 over h, it had a role. It would play a role when we were talking about fluctuations. This 1 over h recorded the co-moving horizon, and then depending on whether the co-moving scale was sub-horizon, super-horizon, it would have different behaviors. And we also talked about the time dependence of this co-moving horizon in a single component cosmology. So if we have just a single component, or we are dominated by a single component with the equation of the states P equals W times rho, then what we have for the co-moving horizon is that 1 over h goes as, so 1 over curly h is 1 over a times the usual Hubble, and this is proportional to 1 over a. H itself is proportional to a to the minus 3 over 2 times 1 plus w. So this whole thing is equal to a to the, so let's see, it is a to the 1 over 2 1 plus 3w. And let me just write his name. So this is co-moving horizon. So what we know is that when W is larger than minus a third, then 1 over h, the co-moving horizon expands, it grows. And when W is less than minus a third, then 1 over h grows in time. Decreases in time. So this is if we plot it, then we have co-moving scale as a function of, say, log of the scale factor, which is an effective time variable in an expanding universe. So we know that if the co-moving horizon is growing, if W is larger than -1/3. So this is log of 1/h. So 1/h, so this omega k, the absolute value of omega k is proportional to 1/h. So this is basically the puzzle that we had before. The fact that omega k, which is proportional to, whose absolute value is proportional to 1/h squared, it grows in time, which means that in the past it becomes very tiny. Now, imagine we had a phase in the past before radiation domination in which omega, we were dominated by some substance with omega less than -1/3. Then the evolution, then this curve would change direction, right? So if we go into a different phase with W less than -1/3, then the co-moving horizon decreases in time. Or in other words, as we go back in time, it will increase. It will increase. That could solve the flatness problem, assuming we have enough, a long enough period in this phase, because we could start from some order 1 value for omega k, and then for long enough period in this phase, it would become extremely tiny, and then again in the hot Big Bang phase and matter domination, it would grow. So that initial condition that we inferred was just somewhere in the middle after of that phase with W less than -1/3. Okay, so therefore this is a way to solve the flatness problem, having the phase with W less than -1. By the way, we can see that. So what do we want really? We want the co-moving horizon H dot, co-moving horizon, which is 1/h. We want it to shrink, which means that curly H itself, it should grow with time. So we want d by dt of this stage to be H to be larger than 0. And this means that this curly H is nothing but A times the usual H, which means that it is just A dot. So this means that we need a double dot larger than 0, which is accelerated expansion. We call it accelerated expansion. Okay, so a long enough period of accelerated expansion before radiation, before the hot phase. So this is the hot phase. And this will be accelerated. All right, now let us talk about the, any question about this part? Okay. How could we solve the horizon problem? We can again look at this diagram. So the horizon problem was a puzzle because we had this initial surface at tau equal to 0. So the past light cone of these patches, they couldn't intersect with each other within this finite amount of conformal time. However, how did we get this fact that the amount of conformal time between last scattering surface and the initial singularity is finite? This was this depends. This is a consequence of having radiation domination in this, or at early enough time, or matter domination. Doesn't matter. Both is in fact it's really a consequence of having W larger than -1/3 in this period. Why? Because let us remember how the range of conformal time is calculated. So conformal time, delta tau between 2 times T1 and T2 is equal to, so this is just a definition of the conformal time, is equal to dt over A, which we can write as integral from A1 to A2. We can change the variable of integration from T to A. So it's dA divided by A dot, that would be dt. A dot is A times H. So therefore it becomes H times A squared. Now again, let us assume that we have a single component. Or we are dominated by a single component. Which means that H is equal to H naught, A to the -3 over 2, 1 plus W. Then this delta tau is equal to integral from A1 to A2, dA 1 over H naught, A to power 1 minus 1/2. So I'm writing it in a weird way, but hopefully it becomes clear why I'm writing in this weird. So now let us imagine that we send the A1, the lower bound of this integration, to 0, right? So we want to go to the initial point when the scale factor becomes 0. Then the question is whether this integral that we have, if I send A1 to 0, so set A1 to 0, so that we call it Big Bang for the initial singularity. The question is whether this integral converges or diverges in in the lower bound. Then we approach the lower bound of the integral. That depends on the value of W or value of this term. So if this term in this part of the exponent, if this is positive, then this integral converges in the lower bound, right? So we have already dA over A. If what remains here is so if 1/2 times 1 plus 3W is positive, then the integral converges. If this is negative, then the integral diverges. So if W is larger than -1/3, then delta tau converges at the lower bound, A equal to 0. If W is less than -1/3, then delta tau diverges. Okay, so here we got this diagram like this with a finite distance between last scattering surface and the initial singularity, because in this period we considered being in matter domination or radiation domination. But if we have a phase before radiation domination, if we have a phase with W less than -1/3, then the delta tau will diverge in the lower bound. What does it mean? It means that the actual conformal diagram would not look like this. There won't be this Big Bang singularity here. That will be sent to -infinity. So this diagram will actually continue to the past. And then these light cones will have a chance to meet, right? So now these points that we said they were causally disconnected, they actually become causally connected in that phase because of that phase, because they pass light cone will intersect with each other. So again, the horizon problem could also be solved by having this phase of accelerated expansion. Any question about this part? Okay, so basically this is inflation, this period of accelerated expansion that we want to postulate before the hot phase is called inflation. And that solves the puzzles of hot Big Bang cosmology. Clearly, it becomes a better solver, or it becomes more efficient in solving the problems if W is much less than or as small as possible. So if W is very close to -1/3, it becomes bad solution, or a solution that takes a lot of time to work. But if it is far from -1/3, then it becomes a faster or more efficient solver of those problems. On the other hand, we have a constraint on W, which is that if we want to satisfy the null energy condition, then W should be larger than -1. So okay, so point number 1, we want the point number 1 is that we want W to be less than -1/3. Point number 2 is that the smaller W makes inflation more efficient. Point number 3 is that W is larger than or equal -1 by null energy condition. So now let us consider a scenario which is called the slow roll inflation, which gives us W very close to -1. So it gives us W equals -1 plus some epsilon. Or with epsilon less than and positive. So this is a very simple scenario that I'm going to explain here that achieves this goal. Gives us accelerated expansion with W close to -. Okay, what is this slow roll inflation? It is, or at least this very simple model of the slow roll inflation is based on having just a scalar field whose energy density is dominated by its potential, and its potential is approximately flat. So I'm going to now go through the details of this, whatever I said now. So we want to consider a scalar field similar to the one that we discussed before, but now there will also be a potential. So let us write the action directly on FRW, flat FRW cosmology. So there will be the kinetic term -1/2 d5 squared minus the potential V of phi. Okay, so now from this action, we know how to derive, or let me just write it more generally. Square root of minus g. So we know that this is square root of minus g in the on FRW is just AQ. And of course, there will be a metric inside here. So we know how to derive the energy momentum tensor for this scalar field. T mu nu is equal to d mu phi minus g mu nu times 1/2 d phi squared plus v of phi. So this we can obtain by just doing the variation of the action with respect to the metric. Now let us imagine that we have so we are on FRW. We just want to discuss the background evolution. For now, we ignore perturbations. Therefore, phi is only a function of time. There won't be any spatial variation. So we have phi is equal to phi of t. And therefore, the non-zero component of this energy momentum tensor are the time component and the diagonal components of the spatial part. Or basically, this T mu nu is going to be diagonal. So what is the T naught naught component of this? That is going to be, let me also specify what the metric is. So it is minus dt squared plus a squared dx squared. T naught naught would be 1/2 phi dot squared plus v of phi. And Tij is going to be delta ij, or let me write it as minus delta ij times so this is delta ij times 1/2 phi dot squared minus v of phi. This is also equal to what we call pressure times delta ij. Okay, so now what is the equation of a state? Well, what is effective W for this? W would be the ratio of P and rho, right? So W is equal to P over rho, which is equal to 1/2 phi dot squared minus v of phi divided by 1/2 phi dot squared plus v of. Oh, by the way, this should be familiar, right? This is just what you would expect for the usual energy density of the field, the kinetic energy plus the potential. Okay, so we get this expression for W, for the ratio of P and rho. And what do we want? We want this W to be close to -1, right? So how do we achieve that? How does it become close to -1? It would be close to -1 if phi dot squared is much smaller than v of phi. Then W is going to be -1 plus epsilon. Where epsilon is So let me write it like this. So if epsilon that I define it as phi dot squared over V of phi, if this is much less than 1, then W is going to be approximately -1 plus epsilon. By the way, this quantity is positive. This epsilon that I define is positive. Any questions so far? About this model?
Just one clarification. The Tij, why doesn't it have the A?
Well, because I forgot to put. Yeah, there should be a square. Thanks. And also here. Any other question? Okay, so let us pursue this. So we want the kinetic energy to be much smaller than the potential. Of course, we should verify that this is a possibility. We can cook up a model that satisfies this condition. So we see that if it satisfies, if this condition is satisfied, then we get what we want. In this, under this assumption, then the Friedman equation, if we ignore other components, if we are dominated by this scalar field, then the Friedman equation would tell us that h squared is approximately 8 pi g over 3 times this V of phi. Okay, and now let us also look at the equation of motion for phi. So this is the Friedman equation. Now equation of motion for phi under this assumption of being homogeneous will be phi double dot plus 3h phi dot equation of motion for phi. So this is just what I obtained by varying the action. Phi double dot plus 3h phi dot plus v prime of phi is equal to 0. So here prime means derivative with respect to phi. Now let us imagine that phi double dot is small. So here the idea is that this field is going to be rolling relatively slowly. Or maybe, by the way, I should have said this at the beginning. Now imagine this scalar field has a potential that has just a minimum, right? So imagine this V of phi just as a minimum with non-zero value. Now, if the field just sits there, then what do we have? We have phi dot equal to 0 exactly, and therefore W exactly equal to -1. So this is just equivalent to having cosmological constant equal to y, equal to v of phi. So this is phi minimum, and we have, because this is equivalent to having cosmological constant equals v of phi minimum. So this will be the extreme situation when we are exactly at W equals -1. Now, we don't want to be at that point for the reason that we want a scenario in which there is some time dependence. We want this scalar field to eventually transition to another phase, which is the radiation dominated phase, right? We want to end this period. So we don't want to sit at exactly constant value for the potential, but it is useful to keep in mind that we want to be close to this scenario. So how do we get close to this scenario? The way we get close to this scenario in this model is that we take the potential which is approximately flat, so the field doesn't roll too fast. So approximately this v of phi is constant, but not exactly. So say the potential is like this. Okay, let's just consider a cartoon. So this is v of phi, and this is phi, and the phi dot is not large. Phi dot is small, therefore we are close to being in being just lambda, being cosmological constant dominated, but not exact, because as phi rose, the value of the potential becomes small. So this is the underlying idea of this model. So now let's consider the equation of motion for the field and assume that it is slowly changing, slowly moving. So then under this assumption, I can ignore this phi double dot term in the equation of motion. I ignore that, I find a solution which I call the slow roll solution, and then we check what are the conditions for this assumption to be valid. So let's assume that phi double dot is much less than 3h phi dot. Again, in absolute terms, which then tells us that phi dot is approximately minus v prime over 3h. So this is called the slow roll solution. So as you see, this was a second order differential equation, but now it has become a first order one. So given the value of phi on this slow roll solution, we also know what is phi dot. Now, what would be the condition for, so we said we want phi dot squared over v of phi to be much less than 1. So let us understand what does it mean for the derivative of the potential. So assuming this is our solution, then we can see that this epsilon parameter is approximately equal v prime squared divided by 9 h squared v of phi. Well, I don't write phi, so v is v of phi. Now, if we use the Friedman equation for h squared, so h squared is approximately given by this quantity. And also remember that we define the Planck mass or reduced Planck mass to be 1 over square root of 8 pi g. So this equation can be written as v over 3 m Planck squared. So we can plug that in here to get v prime squared times m Planck squared v prime squared divided by 3 v squared for epsilon. And this is the quantity that we want to be much less than 1. So what does it mean? It means that the derivative of the potential should be, or v prime over v in Planck units has to be much smaller than 1. So in Planck units, this potential should be approximately flat, which agrees with this intuition. If we want W close to -1, we want this potential, this plateau to be approximately flat, so that it is as if close to being just stuck at the particular value of CC, particular value of cosmological constant. Okay, is the assumption that phi double dot is much less than 3h phi dot, is that assumption justified? Or what is the condition for that to be justified? So, okay, so far we found one condition. Which is called, by the way, it is called the slow roll condition. Now we can look at phi double dot over 3h phi dot. So what is this? Let us, so we want to evaluate that. Let me just evaluate phi double dot on the slow roll solution. So this is the slow roll solution, and we want to see what is phi double dot on that solution. So we want to make a consistency check of our solution. Is this approximation justified? So phi double dot on that solution is equal to minus v double prime times phi dot divided by 3h plus v prime h dot divided by 3h squared. Now, what is h dot? So h dot can be determined from this equation, right? We know h, the relation between h and phi. So if we take the derivative of that equation, the Friedman equation, it gives us 2h h dot is equal to v prime over 3 m Planck squared times phi dot, which tells us that h dot equals V prime over 6 m Planck squared h times phi dot. So therefore, phi double dot divided by 3h phi dot is equal to minus v double prime divided by 9h squared plus v prime squared okay, so now there are a lot of factors, numerical factors. I get the 9, 3 by 3, 9, 54. M Planck squared h cubed. See. Sorry, h to the 4. Okay, and then again, I can use the Friedman equation to get minus v double prime. So 3 times h squared is v divided by m Planck squared. So I get m Planck squared v double prime over 3v, and then in this other term, I will get m Planck squared, and then there will be 6 v squared. So hopefully I did the algebra right. This looks correct. Okay, so we have these two terms. So this is the object that we wanted to check whether it is small or not on this Laurel solution. And that object contains two terms. One of them is this combination, m Planck squared v prime squared over v squared. This is the thing that we already saw has to be much less than 1 for this Laurel condition, for w to be close to minus 1. Now we see that also the second derivative of the potential in Planck units has to be small for this approximation to be valid. And so therefore we conclude that m Planck squared v double prime divided by v has to be much less than 1. So this is another Laurel condition. It's got the second Laurel condition. All right, so therefore with some choices of the potential, which is basically having it relatively flat. So the first condition was that the slope of the potential should not be too large in Planck units. The second condition is that the curvature of the potential shouldn't be too large in Planck units. So under these two conditions, then we can have this Laurel solution, which gives us w close to minus 1. Now, how does the Hubble parameter look like? So we see that what happens is that h dot in this model is not so big. or if we want, if we do it a little bit more carefully, or look at the object which is more interesting. So h dot is given by this expression. So let us look at h dot over h squared. And h dot is negative. This is implied by the null energy condition. So let's just look at minus h dot over h squared, which from that relation and the slow roll condition becomes nothing but so another factor of h, I get v prime m Planck squared, v prime squared divided by 2 so this is equal to v prime over 6 m Planck squared h cube, and then phi dot is v prime over minus v prime over 3a. So we have another minus sign, so it becomes this. So we have v prime squared divided by 18 m Planck squared h to the 4th, which is equal to, so we absorbed factor of 9 times h to the 4th becomes v squared over m Planck to the 4th. So we get m Planck squared v prime squared divided by twice v squared. So the upshot is that h dot over minus h dot over h squared, which is a positive quantity, is much less than 1. What does it mean? It means that h is approximately constant during this slow roll phase. So h is approximately constant, which means that a dot over a, which is equal to h, is approximately constant. Which means that a is proportional to e to the h times t. So we have an approximately exponential expansion. Of course, if we had on just cosmological constant, so then h would be exactly constant, fixed by cc, the value of cc, and we would get exactly exponential expansion for the a. Now it is not exact, it is approximate. But it's a good approximation to have in mind, because now we can check, for instance, how the curvature changes. So how does this model, or how long inflation do we need to, for instance, solve the flatness problem? So let us discuss flatness problem again. So how does omega k change in time? So if you remember, omega k is minus little k h squared times a squared. Now during inflation, this will go as during a slow roll inflation, this h is approximately constant, k is constant. So this goes as 1 over a squared, which is under the assumption that h is approximately constant, it goes as e to the minus 2 ht. Or let me call it delta t. Let's take it, let us relate it to some initial value. So omega k initial times A initial over A, say, final at the end of inflation square. So this is why before I wrote this expression. So if you remember here, I wrote this thing as a square. So we saw that this omega k that we need at the beginning of the hot phase, if the hot phase starts at the Gautier scale, it should be 10 to the minus 28 the squared. Now let us go back to the inflation case. So this is what we have. Omega k got. So say this omega k initial is some order 1 quantity. We want to understand how long inflation do we need until we get to such a small quantity. So now we see that this is approximately omega k initial e to the minus 2h delta t, where delta t is the length of inflationary period. This h delta t, which is approximately log of A final divided by A initial. This is called the number of E-folds of inflation. But because this is it is approximately exponential, so therefore this every unit of HT corresponds to one factor of E. So that's why it is called the number of E-folds. So this is called NE. Number of E-folds. And now if we compare these two quantities, if we want omega initial to be order 1, and we want to get omega final to be so small, then we conclude that the number of E-folds has to be approximately 60 to solve the flatness problem. Any question? Okay, if there is no question, then we'll continue tomorrow at 2. And that will be the last lecture. If you would like to talk to me, one option will be this afternoon during the usual class time. Or you can just stop by or send me an email. Okay, so if there is no question, then I'll see you tomorrow. Thank you.
Thank you.